Good day everyone, we are from Team N and this is our group presentation for Real-Time Software Engineering Assignment 2. In this presentation, we will explain our controller architecture, the implementation in sample drive Python file, the schedulability results from our timing measurements, and our redesign proposal for moving the system towards a physical autonomous vehicle. The main idea in real-time software is the correctness depends on both value and timing. A steering or braking commands may be logical correct, but it arrives too late. The vehicle may already be in an unsafe state. In SpeedTrials2D, our Python controller receives camera input from the Unity simulator and sends back steering and acceleration commands. The challenge is the controller must respond while the game is changing continuously. The game lasts for 3 minutes. The tactical win condition is to collect a net positive 60 green tokens, calculated as green tokens minus red tokens, and also pass every event at least once. Our controller is built using 4 real-time task threads with a declared 5 millisecond period. So, the main question is, can this concurrent task designed to be trusted, or does the timing evidence show that it needs redesign? Our system follows the perceive, compute, and actuate structure. In the perceive stage, read front camera and read back camera receives frames from the front and rear TCP camera streams. These frames are decoded and stored as the latest available camera images. In the compute stage, processing task reads the latest frames, performs HSV color detection, updates event state machines, score lanes, and decides the steering and acceleration value. In actuate stage, send control task sends the latest steering and acceleration into the Unity simulator. The important shared components are shared data, game state, and data log. This allows the task to exchange frame, events, and commands safely without inconsistent reads. These slides show our declared real-time task design. Both camera tasks, read front camera and read back camera, have a 5 millisecond period and high priority. This is because fresh camera input is required before the controller can make a good decision. The processing tasks also have 5 millisecond declared period, but it uses medium priority because it performs heavier vision and event logic. The sense control task is high priority because it directs sense steering and acceleration to the simulator. The real-time task run methods works like a simple periodic schedule. It records the start time, executes the task function, measures execution time, and slips the remaining period if there is time left. This imitates the discipline of periodic tasks in the RTOS. Now, I will pass to Chua Ki-yong, which will explain the implementation and game event handling.
Hi, so I'm Chong Ki-yong. I'm responsible for development for the visual and game rule detection. So, for each vision step, we have the TCP frame decode. So the purpose is we turn the JPEG bytes into OpenCV frames, then the AI can understand. So another is HCV conversion. We separate color from the brightness, then the car can detect the police car. So we have the token mask as well. So we can detect green, red, and yellow tokens. We have also the object mask. We can detect the police chasers and cycles, and we have a golden lamp. We can read the target length and morph before 5 second ends. So there are 3-minute game duration. So we have a golden length. So we have the theoretical objective is we want to have more green tokens more than the red tokens. So include the passing in the event also. So let me go through the function inside. Oh. So let's go through the function in the sample drive function. So the first one, RTT task dot run is run each task separately using the declared period and priority. So read a single camera function to the received TCP JPEG data decodes the newest frame store it safely into the, we call that the OpenCV frames. So processing task is going to read the frame, get the event or token of the police car, update the state and compute the command after detection. So step event FSM is the update police racing car golden lane and event timing step after get the event. So compute control function is used to choose steering and acceleration based on active event, then scope and token strategy. We have a send control task also with pack steering and acceleration as two floats and send them to Unity. So the ascending is we RTT task first, then we'll camera read, then we're processing it, then we have an event and finish state machine, then we have a compute control, and we send the controls. For the event handling strategy, so we have the darkness, police car, chasing A, chasing B, golden light, and tactical. So for the darkness, so the call response we detect the brightness, then we trigger full grade and no staring. Then police car will detect the police avoid collision, so we will not crash with the police car, and collect required grade token. So chasing A with the real camera, confidence trigger, defensive movement. Chasing B with maintain speed and avoid danger land. So for the golden land, we will detect the land instruction and arrive within 5 seconds. So tactical, we target like net the 60 green tokens while passing every event. That's all, thank you.
Now we move on to the timing analysis. This table shows the measured execution time from a 30-second live capture. The values are in milliseconds. For read from camera, the average time is 18.96 milliseconds, and the WCET is 113.55 milliseconds. For read back camera, the average is 18.967 milliseconds, and the WCET is 114 milliseconds. The processing task has an average of 11.64 milliseconds and a WCET of 59 milliseconds. Send controls is much lighter, with an average of 0.28 milliseconds and a WCET of 1.79 milliseconds. The key finding is that the declared 5 millisecond period is not achieved in practice. The camera tasks are separately affected by socket and frame I/O delay. To analyze schedulability, we use the utilization formula U equals the sum of C over T. Here, the C is the measured worst-case execution time, and T is the declared period. Since all 4 tasks declare a 5 millisecond period, the measured utilization becomes approximately 57.86. For 4 fixed priority periodic tasks, the Liu and Leyland rate monotonic scheduling bound is 0.757. This means our measured utilization is about 76 times higher than the sufficient IMS bound. The conclusion is important. The controller may be functionally usable in a simulator, but the declared 5 millisecond task set is not formally schedulable. This is the strongest link between our simulation measurements and real-time scheduling theory. For the case study, we referred to the 2026 autonomous vehicle perception work by Saranya, Achana, and Rishi Kaushik. The system uses a ZED2i stereo camera, a quantized YOLO V8N neural network, Jetson Orin Nano hardware, and ROS2 integration. The system has 150 millisecond soft inference deadline. The results show that 98.11% of daytime frames meet the deadline, and the deadline violation is bounded below 30 milliseconds. The important lesson is that real autonomous vehicles workloads may also exceed textbook RMS or EDF feasibility. However, professional systems measure lateness, bound it, and treat it as part of the safety argument. I'll now pass to Wang Yaping for the benchmarking, redesign, and conclusion.
Hi, I'm Wang Peng, and this slide compares the case study with our SpeedTrial2D controller. The case study uses just an only normal embedded hardware, while our controller runs using desktop Windows servers. The case study uses the ZD2i30 camera, where our simulation receives camera image over TCP socket. For perception, the case study uses Critical YOLO VAN, where our controller uses HSV segmentation and finite state machines. The case study has 150 milliseconds of deadline. Our controller declared a much take 5 milliseconds normally per door. The most important difference is overall handling. The case study used the deadline penalty model with our current RT task current does not explicitly count deadline mistake. Therefore, our redesign should make timing fail visible, means usable and recallable. In this page, our redesign proposal focuses on making the control more realistic for physical deployment. First, camera input-output should be non-blocking, so waiting for camera data doesn't not block the control path. Second, the system should use double buffers. Each camera task writes the news list frame into a buffer, but the processing task reading the most recent completed file. Third, experiences event directory should be created. A triple low resolution check should run first, and for declaration should only run when inviting existed. Fourth, task approval should be based on a measured WCET, not only normal value. The RT task carrier should also count the deadline missing experience in CT. The physical sensor we propose a CPAT vision stage camera, LIDAR, and LiDAR data with enter through single task. Then a functional task would push on-field game stage for the control task. For physical vehicle, manual observation is not enough. We need time evidence. First, WCT between marking should be performed using worst-case scenes. These scenes should include the dance token and all major events, so we can record the maximum extreme time, P9 time, and dynamic missing. Second, hardware in load testing should run the control on the target, embedded both with ray interface, with the vintage dynamics and stereo simulate. This helps reveal inter-report latency, resource contention, and spatial duty. Third, safety sensitive must be defined. Example includes unsafe jetting, still signal data, and long gaps between control packets. If the system closes the throw should issue inter-fallback model. For example, it can break, hold LAN, and disable real leak until time becomes safe again. Thank you.